My name is Nathan Thwaites, and this is my lab for Physics 2211 about oscillations. Introduction. The system for this lab was a weight with a mass of 0.402 grams, and it was attached to a spring which was attached to a fixed point. The surroundings for this lab was the spring with a constant of 6.83 and an L naught of 0.123 meters, which was attached to a fixed point above the weight. Gravity and the Earth are also involved within the system. The fundamental physics principles to know to complete this lab are work energy principle, momentum principle, position update formula, Newton's second law of motion, and the equations for kinetic energy, potential energy, and gravitational and spring energy. So this was the information given for this lab. In the experiment, we had a video, and I used a tracker to analyze the motion of the mass spring system using computational modeling and the point mass software within Tracker. I copied this into a CSV file without including the time, ensuring that only the X and Y positions were included. And I used a glow script to model the computation of the energy graphs according to the X and Y directions using the system's behavior observed from the video. Additionally, I plotted changes in kinetic energy, gravitational potential energy, spring potential energy, and total energy over time to assess whether the energy principle was satisfied. And then lastly, I estimated the oscillation periods from both the X and Y position data and compared these values to further analyze the system's dynamics. So this is my code and graphs. The graph is containing information about change in energy over time, and then setting the resting spring length, K value, the L spring vector, as well as the initial values for potential gravitational and spring energies, which you guys see all on the left, and then the calculation loop in the bottom, which through the momentum principle and work energy principle, setting new values for velocity position and new kinetic/potential energy for the entire model. And then these last two graphs on the right are containing information about the change in X and Y position over time. In other words, computation versus experimental position. So then, for the model, is the energy principle satisfied? Justify your answer. Yes, in this case, the energy principle is satisfied because the total energy, the potential, and the kinetic combined remains constant throughout the duration of the experiment as shown by the energy graphs in the computational model. In this way, the network or the net external forces in relation to the object's displacement acting on the weight is shown to be equal to the change in total energy of the system, accounting for both kinetic and potential energy. Next question. Using the data you obtained in Tracker, make two separate estimates of oscillation periods. First, by estimating the period of oscillation from the X position data, and second, by estimating the period of oscillation from the Y position data. Compare the two estimates and discuss it. Well, the T, or the oscillation in the Y direction, is 1.709 seconds, and I calculated this by finding the point at which the motion repeated itself roughly, and it happened to be about 1.7 seconds in the Y direction. And then for the X direction, it was approximately 1.519 seconds. And just like with the Y, I calculated the period for the X direction, and it seemed to be smaller, most likely because of the direction of the force throughout the object's motion. While the motion in the Y direction was largely due to the force of the spring and gravity on the weight, the X direction movement was dictated by the starting position, or more specifically, the spring force in the X direction. Due to the angle of the spring during the start, given that it wasn't perfectly vertical, it made sense that the weight had motion in the X direction, and that its motion was also sinusoidal for the same reasons the motion in the Y direction was sinusoidal. Conclusion. The physics principles that I applied, the energy principle, the Newton's second law, the oscillatory motion, using which applied Hooke's law, and then the key takeaways were that successfully modeled and visualized the ball's oscillatory motion using Python and VPython, demonstrated the relationship between the spring's potential energy and the ball's kinetic energy during the oscillations, reinforced the understanding of spring mass systems and the real-world applications in oscillatory systems, and we validated the computational model by comparing it to the experimental data and video analysis.